What's up? What's up? What's up? Sorry about that. So thank you, Skylar. And thank you to Gush. Gush is a really cool organization that I wish was there when I was an undergrad. So very cool to be a part of this and glad to see kind of the community amongst statistics people. So hello to everybody. I'll give you a quick introduction. I know Zoom stuff can be a little bit brutal. I know especially learning code over Zoom can be hard and difficult. So we're going to try to make this as fun as possible, as interactive as possible. I know everyone says that, but just, interrupt me with questions if they come up. We'll try to make it interesting. And this is being recorded. And I also shared a lot of other resources in email. You can feel free to click through. You should have this code as well to play with on your own. And in general, those resources will be able to help you. You can always reach out to me if you have questions about that stuff. So we try to make this as good as possible. I know it's a Friday afternoon and all that. So my name is Matt, as Skylar said. I was in your shoes. I started college in 2013, 2014, graduated 2017 in statistics, came in thinking I wanted to do economics like many Harvard students and took Stat 110, really liked it and went from there. Really enjoyed my time in the department. I TF'd a bunch, TF for 110 and 111, which, obviously is why I'm helping out here with the R stuff, as well as 104 and 171. So just have seen a lot of different parts of the kind of stat process. We're going to be doing, and I guess I worked in New York for a couple of years after graduation, and now I'm back doing a PhD at HBS. So I'm just across the river from you guys. I actually met Skylar to a class together last semester. So long story short, always feel free to reach out with questions or sort of anything that comes up. Okay, so we're going to be doing R today. I've got this R studio in front of me. I'm told that, there's been some debugging efforts. So everyone maybe hopefully has something like this in front of them. I know it's like weird to look at. We're going to talk through what it means. I just want to motivate our session here with two big points. One is that the power of R is really worth the steep learning curve. I'm going to assume that you haven't seen a lot of coding before. And learning coding is difficult. Learning coding and all, it's a very steep learning curve. And at times you'll be doing things that you feel like are very simple and very easy. You're like, why don't I just do this in my calculator? Why don't I just break out my T184 or whatever? I don't know if you youngsters still use this, but I love this. It's never far from my reach. Or why don't I just go to Excel, and do this in Excel? And I promise that once you get past that steep learning curve, which takes time, you'll find that R is super powerful, super flexible, that you can do things that you couldn't do otherwise. So that's the first motivation. The second is that, there's a lot of ways to learn these things. And unfortunately, I think a lot of the ways are not super helpful. Even this video, or, even this session, it will be helpful, but the best way for you to learn is to do it yourself. And the best way for you to do it yourself is to come up with a project. Maybe it's like doing some sports analytics or doing some data set online that you wanted to crunch or do some analytics for. And if you use R to make some charts or do some simple analysis, or even Stat 110, most of you are fresh out of 110. Let's say you're not convinced that the Monty Hall problem is correct. You can use R to simulate it and check. And not only will that reinforce your understanding of probability, it'll reinforce your skill in R. So instead of, just kind of watching other people do it, which is a good place to start, actually engaging in it will help you to learn. And the other thing is 111, if you don't have any R experience, Stat 111 will be a lot easier if you spend the next week or so before the semester really starts getting up to speed in R. Because I remember when I took 111 my sophomore spring, I had no coding experience, and the first couple of weeks were a real struggle to learn both the inferential concepts and the R concepts. So hopefully that's a decent, like, so I'm just seeing what's going to say. Okay, cool. Hopefully that's a decent motivation as to why we should be here. And now we can actually walk towards the coding stuff, as I mentioned, and I think Skylar just said, interrupt me, thumbs up, yell at me, whatever, if you have questions on stuff. So what we're looking at here is R Studio, and R is the language. It's the actual like coding language that, is running kind of all this stuff in the background. R Studio is the GUI, the graphical user interface, that basically allows you to interact with R and type R code and run it and all that stuff. So I know it can look a little bit intimidating at first, but once you get used to it, it actually becomes very comfortable and easy to use. We basically have 4 panes here, and this top left pane is where we type our code. So you can see I have some code here, and I have a bunch of files with different code that we're going to go through. But I have some code in the top left, and the top right is the console where the code actually gets run. So we're going to go through this second, but if I highlight some code in my script editor in the top left, and I select it and hit enter or whatever, control enter, it's going to run on the top right, and you can see it did the 4 + 4 is 8. So where I keep my script and where I run the script here, the default like arrangement of the panes is slightly different. I changed it so it's like this, but you'll see something similar to that. The bottom left is kind of your environments, your environment and history and that sort of stuff. So we're going to start defining objects, defining things, making charts, and on the bottom left, that we'll start to keep track of like what we actually have running in our system. Currently, the environment is empty because I started a new session, so there's nothing in there. The history is just the code we've run. So you see we ran the code 4 + 4. R keeps track of every keystroke you make, which is a little bit creepy, but also good in case you want to go back. If I just double clicked on this 4 + 4, you can see it shows up in my console, ready for me to run again if I want to, which I will. And now you can see in my history, it showed up again. So nice little feedback loop there. And then the bottom right, mostly used for plots, also for some like help package things. So we're going to get into plotting, but let's say I want to just make it quick. Say I want to do a histogram. I want to just make a quick plot. It's going to pop up right in the bottom right. So, and it's really cool. You can export it, copy it to the clipboard, take a screenshot, whatever. So bottom right is mostly for plots as well as some help stuff, which we will see, but I'm going to clear it for now. Okay, so let's actually get into the code. I think the first, you can see this file is called intro. I think the first best way to think about, first, are there any questions before I go on? Cool. I think the first best way to think about R is as a calculator. I remember doing PSET 1 or 2 and Stat 111, and I'd be doing a calculation, and I'd be using like either my handheld calculator or Google or something, and then kind of realizing that I could. It's very simple, but realizing that I could do this stuff with R. So here I just have code 4 + 4. It's sitting on a line, and I can just move this thing, and I can click this run button up here, and it will run in my console. I could also go to that line on my keyboard. I'm hitting Control Return, and it runs on my console. So in its simplest, R is just a calculator doing arithmetic. If you want to think about it like that. This next line, line 4, and R is nice because it kind of numbers the lines like this. Line 4, you can tell what it says. It says this is a comment, and the way we know it's a comment is because, first of all, it's in italics and it's in a different color, and it starts with this all-important hashtag. If I deleted this hashtag, I would see this is a comment in the same lettering as the other code. I would get this weird error, which we'll talk about in a second, because right now R is interpreting this as code. And you can probably guess this is a comment. If I run it, it's going to get an error because it's like, what code is this? This doesn't make sense. Basically, comments are used for humans. If I highlight this line and run it, it's not going to, it'll like run in my console, but it's not going to compile. Nothing's going to run. There's going to be no errors. And comments are for humans. So if you write a script and you want to leave notes to yourself, like, what did this chunk of code do? What did this chunk of code do? If someone else is going to be reading your code, that's super important to comment, so you'll see these hashtags in different code, and that's what it's for. We're going to see it a bunch in today's session. So I think those are the two most simple like applications, is just adding things and writing comments. Like if I wanted to say multiply, that's a comment, and say I want to multiply 7 times 8 and raise it to the power of 4, and I got this number here, right? So very simple calculator annotation stuff. So that's base, step 0 for R. I think the next important step is assignment. And this gets to actually saving things in our memory that we can use later. And I think this is an intuitive concept. We want to save a quantity as some variable, as some object, and then come back to it later. So you can see here, I have this in line 10, in line 11, I have this very like familiar y = 5. And you can imagine if I run this, so you can see I ran it on the right. In my environment, all of a sudden I have something in my environment, the variable y equals the value 5. If I type y in my console and run it, I'm going to get 5. If I do y times 8, I'm going to get 40. So really nice. Like, obviously it's easy to type 5, but what if y was like 10,407,000? You just save it as y. It's kind of nice going forward. So that's what the y equals is. This X arrow hyphen thing is for. Does anyone know what this will do if I run this piece of code? If you don't know, you can guess. Or you can run it on your own session and see what happens. Okay, I'll give you guys a pass because it's early, but I'm going to be asking a lot of questions. So be prepared. Be prepared to answer. If I run this, it's going to do the exact same thing. It's going to assign the value 4 to X. So if I run it in my console, I type the value X, I get 4. Value, the variable X, the value 4. However, instead of this equals, we have this weird like little arrow thing. And even though you're probably familiar with equals, if you do Python at all, Python, it's all equals. In R, we use this assignment operator. They will mean the same thing, but you're going to see it's just very standard convention to do the assignment. I'm not really sure what this is for. I've heard a lot of things. I've heard, personally, I think it's easier to search through your code if you have the equals. I saw a chat. Let me make sure the chat. Oh, assignment. Nice job, Alan C. Wang. Alan C. Wang got it. Sorry, I have to be better at reading the chats. So if someone knows like the real reason for this, for me, it's easier to read through my code if I, the equals will be used for different things, which we'll see, and the assignment will be used for assigning things, which is good to remember. Sometimes, this is another, it may seem very obvious now, but what if you had 5 equals y, right? And it's unclear like what the direction of assignment is. Like, are you putting the value 5 into y? Are you putting the value y into 5, which doesn't really make sense? The nice thing about this arrow is that it tells you exactly, I'm going to make my screen a little bigger. It tells you exactly which way the direction of assignment is going. You're putting 4 into X. So those are the 2 reasons that I usually say y is 4. Someone may know better, but you're going to be using this and seeing this as standard convention. So anyways, we've saved both X and Y. You can see it's in our environment. If I run X, I'm going to get 4. And if I do X times Y, what am I going to get? This is a softball. 20. Nice job. Oh, we got multiple people saying 20. Thank you, Zad Chin and Jason W. Wang, one of the 2 Jason Wangs on this call. So if I run X times Y, correct, I get 20. So that's it seems like we've basically done nothing, but I think it's important to be comfortable with these ideas. My first couple weeks, I would just use numbers and I wouldn't save them, and I have to copy and paste the numbers and like copy them to the 10th decimal and all that stuff. And so just use assignment, just save variables. It seems very simple, but it's good to kind of know. So this next line on line 18, R is really cool because it's an open source package, which means that people have written a lot of code for R. It does a lot of really cool things, and all of us can freely access it and download it and use it to do the cool things we want to do. So most of the time when you're doing stuff in R, like all the stuff I've done up here is very basic and standard. It's in base R. So when you download R, it just comes with it. But a lot of the cool stuff we want to do we're gonna have to use libraries that have been, they're called packages or libraries that have been built by someone else. And the way we load it into our system is with this library command. So we're going to talk about ggplot2. Some of you may be familiar with it. It's a package to do visualizations, really beautiful, powerful visualizations. We're going to talk about it. You can see it, kind of on the top. We're getting there. But if I want to load like the package and all those capabilities, I just run library ggplot2. And now it's in my system. If I type ggplot2::, this is a little bit more advanced. We'll get to it. But this is telling me all of the functions that I can access from the ggplot2 library. So super useful. If you run library ggplot2 on your machine right now, you're going to get something like this, where it says there is no package called ggplot2. I just typed in a random word. There's no package called that. So what you have to do before is install packages ggplot2. I'm not going to do it because it's already installed, but if you run this install packages function, you only have to do that once, and then it's in your system, and then you load it to the front of memory or whatever. I'm not like a good computer knowledge person, but you install something with ggplot2 and then you call it with library ggplot2. So that's kind of how you load packages in. And then the last important thing is how to get help, right? Google is your number one. Stack Overflow. I mean, you guys are undergrads studying STEM stuff. You know what it's like to just like Google for a long time to try to, figure something out. So I don't have to tell you that like Stack Overflow is your friend and you're going to see a lot of really useful answers there. Within R, you can get help just by typing question mark and then the thing you want to ask about. Usually they're functions, which we'll talk about. In this case, if I wanted to learn more about the function mean, which takes the mean of a bunch of things, I would do question mark mean. And on the bottom right, as promised, under the help section, it'll pop up. So we get, the description of the function and all this useful stuff. Sometimes if you have like a function that's not preloaded in a library that you have preloaded, you'll need to do double question mark and it will come up. In this case, this is doing a full search of R. So it's doing a full search and saying, okay, where are all the, the means? And in this case, this is the mean we want, the mean in the base package. So I would click on that. But that's how you get help in R. Okay, so this may have been super basic for some people, super obvious, maybe not for others. We're going to keep kind of going at this pace. Do we have any questions before we move on to looping, which is actually like using this stuff together to do something interesting? I see a chat. So that's a good question, Clara. Clara, sorry if I'm saying your name wrong. Oh, sorry, that's a direct message. So I got a good question saying, what is the functional difference between the console and intro R? This might not be like the like totally technically correct computer science answer, but basically the top left, you can think of it as a Word doc where you write up all your code and you save it, and you're going to save this file and you save that file in your downloads or whatever. The console on the right is where you actually run that code. It's like the battleground. It's where, the code gets put into. On the left, I'm just typing everything up, organizing it. And then on the right is where it kind of gets sent to actually be run. So that's the difference. That's a good question. And there's definitely a more technical answer, but that's how I think about it. Okay, another good question from Richard. Is there a way to hide the output like of an assignment from the console when you run a line of code? That's a really good question. So like, let's say, you have a lot of code, but a lot of it is obvious, like this X4 being assigned to X, you don't want to show that in your console because you don't care. It's just like excessive. It's not a big deal here, but if you have like 100 lines that you don't want to see, I don't know if there's definitely a way to do that in R Markdown, which we're going to talk about. That's actually like making reports in R. I'm not sure if there's a way to do it in your console. That's a really good question. There might be. If there is and someone knows, feel free to speak up. But I'm not positive. But it's something that definitely Stack Overflow would be able to answer. And it's a very good and intuitive question. So thank you, Richard. Okay, don't see any more chats. We're going to go to loops.r. So by a show of, I guess, thumbs up or something, how many people have seen loops in computer science? Okay, good. I see some thumbs up. That functionality works. Good. Okay, so most people have seen loops. So this may be a bit of review or just learning the syntax for it in R, but there definitely were, about half people haven't seen loops. So we're gonna go through it regardless. So looping is kind of what it sounds like. We're gonna be following a loop, doing something over and over, a specified number of times or whatever. And this really allows us to harness the power of a computer. You can ask a human to do something over and over, but they can't do it that fast. They're going to get bored. They're going to get tired. They're going to make mistakes. A computer can do something a million times and not complain and ask you, what you want to do next. So that's why we really want to harness the power of computers for this. And this is what I'm talking about, kind of the start of the power of R. So first, I'm going to initialize a vector. And now we're kind of jumping into more advanced concepts. You can see here I have a comment. That comment is telling me what this line of code is doing. I'm going to run this code. This here, and I guess this is also the introduction to functions, which we're going to talk about soon. The ordering of that is a little bit off. Actually, let me just okay, we have functions. So let me think. Yeah, so a function basically is some tool. I like to think of them as tools that do stuff in your code. And the way you call a function, let's say we use the function mean, the way you call a function is by writing the name and then writing a bunch of, the parentheses. And then you want to like take the arguments of the function or where you're actually going to run it on and put it inside the parentheses. So let's say I wanted to find the mean of 1 to 10, this like this like colon thing basically establishes a vector from 1 to 10. So let's say I wanted to find the mean of that 1 to 10, I get 5.5. So call the function, and the arguments inside of the function are, what we actually run it on. Functions are obviously super important. They're the building blocks of R. In this case, we have the rep function, which is the replicate function. I can type $rep, and you see replicate elements of a vector. It takes 2 arguments. It basically says what we want to replicate and how many times we're going to replicate it. So if I run this piece of code, we're replicating NA 10 times. And this is a vector, which, you've probably heard of, at least in Stat 110. I'm trying to think of when a vector comes up in Stat 110. They probably like any sort of Jacobian transformation where you have like a 2x2 vector, whatever, multivariate normal, bivariate normal, that's kind of a vector. If you've taken linear algebra, of course, you've seen it. And in this case, we have a vector of length 10. It's 1 row, 10 columns. This NA is a very important like object in R. It basically, I think it stands for not available. And like if I tried to take the mean of this function, it would say NA. If I tried to do the variance, NA, because it's not available. Like I'm trying to, these are basically placeholders for the numbers that we're going to put into our vector. So it's nice to do this. It seems a little bit weird, but we're going to fill this vector with random numbers. Let's say we messed up and we only filled it halfway, right? Then we would know that the rest of we'd see the rest of our vectors NA, and that would be a sign that, okay, we messed up. We have to fix that. So that's why we pre-fill it with NA. Okay. So one more thing about vectors. Let's say I wanted to index into a vector. I use this syntax. I use the square brackets. So instead of the parentheses which we use for functions, I use the square brackets and the index I want. So I do x4, and it's going to pick out the 4th element of x. In this case, that's this element. They're all the same, which is why it's going to be NA no matter what. I could also pick out the 4th to the 7th element, and I get 4, 5, 6, 7. So that's how I kind of index into the elements. So that's all we need to run our for loop. And our for loop is here from lines 4 to 7. And the for loop is pretty cool. The syntax here, if you've seen it before, it'll be familiar with the syntax. This is saying, and you notice when I type 4, it turns a different color of orange because it's an important thing in R, as well as in turns a different color. So we are looping for or from 1 to 10. Okay, so we're looping from 1 to 10, and the thing that's changing each loop is I. So the way that I think about this is, this is telling us we're doing a for loop. We're going from 1 to 10. I is what's changing. And then you have these curly brackets here, and you're actually doing stuff. You're running your code within the curly brackets. So that's a little bit weird. Hopefully it makes sense once we actually do the example. So we're saying we go through this loop 10 times. I see a chat. I'll look at it in one sec. Go through this loop 10 times from 1 to 10. And the first pass to the loop, I equals 1. The second pass, I equals 2. Third pass, I equals 3, et cetera, et cetera. Oh, really good question from David. David asks, is it convention in R for indices to start at 1 rather than 0? The answer is yes. So if you've done other computer science, you might have seen 0 indexed. Python is 0 indexed. The first element in X would be x0. If x0, if you do that in R, you're going to get what? R is basically saying, what do you mean? The first element is always 1. I prefer that. I know hardcore computer scientists prefer the 0 index, but it's annoying if you have to go back and forth. But just this is called the first element. The first element, second element. This is not the 0th element. The first element, the second element starts at 1. Really good question. Thank you, David. Okay, so now can anyone tell me in the chat or whatever what they think this code is going to do? So I'm going to run this, and I'm going to hide the bottom because you can see. What do you think now is inside of X? What do you think X is? If I type X and run it, what am I going to get? Nice. Awesome. Alan C. and Jason W. Thank you guys. Both correct. You're going to get the integers from 1 to 10. And the reason why is because you go through the loop the first time when X is 1. So you're saying the first element of X, remember this is X index, 1, I equals 1 in the first pass, and we're assigning 1 to that value. We loop through the second time. Now I equals 2. So the second element of X is 2. Loop through the third time. The element is 3, on and on and on. If I type I into my console, it's going to be 10. And that's because we just finished running the for loop. the last, value of I is 10. And if I do x10, I should get, or xi, same thing, I should get 10 because that's the 10th element. Now, you always have to be careful about like where you start and end when you're running the for loop. If I did x1 to the 15, I would get, something different. And okay, so R is luckily nice if you do, you're not going to get a weird error. But we initially like set up our vector to have length 10. But if I say that I should go to 15, I'm going to get a vector of length 15 out, which is something that I didn't want. So you have to be careful of where it ends. If I did I from 1 to 3 and I printed X, then you're only going to see numbers from 1 to 3 because the numbers from 4 to 10 weren't touched. We exited out of the loop while I was still 3. So this is a case for the NAs to be helpful because there's something you didn't fill. Okay, so hopefully that makes sense for a simple for loop. You see, okay. Now we're going to do another type of for loop, a little bit more advanced. We're going to use some stat 110 stuff. So again, we're going to create a path for Z. In this case, sorry, that's X, not Z. In this case, Z is the same structure. It's a bunch of NAs, but it's 100 times instead of 10 times. And in this case, I'm going to initialize Z at the first element. So I'm saying this is the first element of Z, and I'm going to assign this thing R norm 1. Who wants to tell me in the chat or whatever what they think this R norm 1 is? Nice, exactly, Alan. This is the standard normal. This is a random draw from the standard normal. We're going to talk about random draws and simulations later on. You might be thinking like, how could a computer do something random? And we'll talk about that without getting close to like determinism or anything philosophical like that. But this is a one random draw from a standard normal. If you wanted to investigate this function more, you would do question mark R norm. The R stands for random. The norm stands for normal. There's a bunch of different similar functions, but here we're using our norm. The first argument is n, the number of draws we want. The second argument is the mean. The third argument is the standard deviation. In this case, this syntax means that the default mean, if we don't enter a mean, is 0. The default standard deviation is 1. So if we don't tell R what we want the mean and standard deviation to be, it'll default to a standard normal Z, which you've seen, in your 110 travels. That's why I call this thing Z. So, if I type Z, I'm going to see my first value is a draw from pretty big draw from a standard normal 1.1.5. So clearly it's everybody's lucky day. Okay, so that's the first value of our path Z. Now we're going to have this loop that goes through, and everyone just take a quick look at the loop, and then posit a guess to what this loop is going to be doing. You can do it in the chat. Extra points for succinct answers. Nice, exactly. Thank you, yes. Okay, good. Everybody stop typing. No, I'm kidding. This is good. This is really good. Thank you, all those answers. So the first answer, Gerald, perfect. That's correct. Everyone, yeah, and Richard, that's exact. So all these are right answers, and I was looking for like random walk or Brownian motion. This is technically Brownian motion, but this is sort of a random walk over time. So thank you everybody for chiming in. That's great. So we at our ith time to the loop, we're taking the ith index of Z. We're adding on Z, the ith minus one index, whatever. The previous index, we're taking that and we're adding on another random normal draw. Okay, so we're going to run it. And notice that I have to be really careful about my, where I start and where I end. I'm starting at 2 to 100, because if I start at I equals 1, what's going to happen is I'm going to have the Z index of I minus 1. 1 minus 1 is 0. And if I do Z of 0, we get, this is saying I have a number that's length 0. Doesn't make sense, not going to work. It would work, but it would overwrite. It would overwrite the first element, which we might want to do, but for this case, I'm just kind of walking through how a loop for loop works. That's why we're doing that. So this is going to be a random walk. I run this, and we're going to see Z is this random walk that bounces around over time. And we're going to talk about plotting, but I can plot this just so we get a sense of what it looks like. And you can see there, beautiful walk of Z over time, positive for a bit, dips negative, and then kind of comes back. But this is, still simple, but obviously a bit more advanced than just assigning, the ith value of X to I. In this case, we're actually like, taking a previous value and adding it on. And I think Neil Shepard is teaching 111 this year for you guys, and he loves time series stuff. So, you might see this structure a bunch. So it's simple, but hopefully that makes sense. Okay, so that's kind of everything we're going to do for loops. You can imagine, and I think we're going to do some examples where the code inside the brackets can be way more complicated. You could have thousands of lines of code within the brackets. You can make it as insane as you want. You could have other for loops, all this stuff, but if you understand the basic structure, then the world of complexity opens up for you from there. So let's talk about the other major type of loop. I think there might be another one, but I can't think of any others. The other major type of loop in R, which is the while loop. So you're more familiar now with for loops, so I'm just going to kind of talk about what this means. The for loop loops for I from 1 to 10, or I from 2 to 100. The while loop will loop while some condition is true. So in this case, I type while, you notice it turns orange. And then inside the parentheses, remember in the for loop, we had this like from 2 to 100. Here, we're looping until this condition is not true. You might see like X less than or equal to 3 or something. This is a condition, and we should go over like how this logical stuff works in R. As you would expect, if I type 2 less than 3, it's going to say true because that's true. If I type 2 less than 1, it's going to say false because that's false. If I say 5 plus 5 less than 11, which is true, and 9 greater than 10, this is going to say false because, this one is true, but this is false. So true and false, if I type true and false, this is going to be, this is going to be false. So these are logic, stuff that you hopefully are familiar with in like some sort of capacity. It's the same in R, it's just kind of how it works. True and false are just represented by these capital like block letters, just capital letters. You don't have to do anything special. And the other useful thing is or. So if I do 5 plus 5 less than 11, or with this vertical bar, 9 greater than 10, that's going to be true because this is true, this is false, but we're asking true or true, and it's true. So that's if I do true or false, it's going to say true. So that's kind of what's going on here. So every time through the loop, we check if this condition is true. Now I just typed true here. Can anyone tell me that's kind of a tough question. So now that you kind of I've talked about the while loop, look at this loop and then tell me in the chat when this what the idea here is, or when it's going to stop, or what I'm trying to get at. Awesome. Thank you, Stephanie. That's exactly right. The loop will always run until it's broken with break, which is exactly right. Also right. Yeah. And that's a more specific answer. Thank you, Gerald. So the loop will always run because true is always true. If true isn't true, then we all have to go home because I guess everybody is home, but we all, it's very sad if true isn't true. The world is over. So true is always true. This will always work. The way we get out of it then, usually if like X was like I did this till X less than 1/2, this will run and every time it will check. And when X is not less than 1/2, it will break. But if I just put true in here, it's going to run until it breaks. And you can see I have this break condition here. Another time to introduce two more important parts of R, the if condition and then the break condition. You can see both of these turn orange, and means they're important. So here I'm saying, first I'm going to draw X and Y from a random uniform. So you guys all remember the unif 0, 1. You probably remember universality uniform, one of the hardest parts, I think, in 110, unfortunately, because it actually is pretty simple and very powerful, but it's difficult to wrap your head around. I don't think it showed up. I like perused the 110 final. I don't think it showed up a lot. So everybody made it out, but maybe I missed it. So everybody made it out alive from universality. But these are drawing one draw from the standard uniform. Again, if I do question mark R unif, this is a random draw from uniform. The number of draws, the min and the maximum here, the default is 0 to 1. I could draw from 0 to 100, 10 to 40, whatever. So, here X and Y are random draws. X is about 0.2, Y is about 3/4. And then I'm going to see if X plus Y is less than 1. So, you can see how the expectation of X plus Y is 1. And you can kind of think about, actually, is X, I don't want to say this wrong. Yeah, X plus Y is uniform from 0 to 2. I didn't want to say something that wasn't right. So X plus Y is uniform 0 to 2. So you want to break when that uniform 0 to 2 is less than 1, which will happen about 50% of the time. So I'm going to run this, and it's going to check every time if this condition works. And if I run this and it ran, you can see I have this kind of, it ran, and now I have this new caret here asking me to do something. If I type X plus Y, it's gonna, it's gonna say that, yeah, this is less than 1. Like X, and Y, these are less than 1. That's why it broke. So I just want to show you guys something pretty cool. Can you see chat? Yeah, really good question. Thank you, Lindsay. Lindsay asked, does this save X and Y as a value or as a random variable? So the randomness is coming, the randomness, we'll talk about what random means in this context later. The randomness is coming from this function, RUnif, that draws a random value. If I ran it again, it'd be a different random, different random value. If I did 10 random draws, it'd be 10 random values. But when it runs, you can think of trying to think of the 110 concept. You can think of random variables as a function, a mapping from a sample space to the real line. You can think of this RUnif as doing the crystallization from the sample space to the real line. Once it runs, you get that value, and then you store that value in X. So X and Y are values, not random variables. They're crystallized versions of the random variable. It's nice. Obviously, it's fluent with 110 literature that they're lowercase here. Everything is lowercase pretty much, but it works out. It's not a random variable value. So that's a really good question. So thank you for that. So I just want to show everybody one cool thing before we go to the next section. Okay. Okay. So I'm going to set I, this variable I equals 0, and every time through the loop, I am going to add 1 to I, and that tells us how long we had to wait for. So, let's do our original example, X plus Y less than 1. If we run this, I get I, and look at that, it only had to run once, and it found, a solution. If I run it again, also once, sorry, when I equals 1, it means it ran twice. When I equals 0, it means it ran once. It's not that important. I'm probably just confusing everyone. But what I wanted to say is, what happens if I set this to be the condition, X plus Y less than 0? What's going to happen in this case? So I will set this to run, and then I will ask everyone, and then chat and put in the chat what you think is going to happen. Won't break. Thank you, Caroline. Thank you, Richard. Loop never terminates. Alice, run indefinitely. Exactly. So you can tell this is still running. There's no caret here to say this is over. I'm going to hit escape to stop it. Does anyone want to guess how big I is? I'm going to put the I here. And behind this. Any guesses as to how large I is? How many times it's ran? Okay, I see no guesses, so I'm just going to type it. Whoo, look at that. It ran 3.5 million times in the time we were just sitting here. So that's just fun. There's no reason to show that. I think, one reason is that you have to be very careful with your conditions. Because otherwise you're going to get into a loop that goes forever. And, R works very, very fast. This went through 3 million times, which is, crazy. So you have to be careful about your conditions and how you set it up, or you're just going to set R spinning forever. And that's not good for everyone. Anyway, okay, so that's everything with loops. Anyone have a question before we move on to some visuals? We're making good time. Okay, seeing no questions, I proceed. Okay, so yeah, this is good. Okay, so we talked about and had some good questions about the randomness, generating random numbers in R. Here, we're going to get a little bit more into it before we, talk about simulation in a later script. So, I think the concept of randomness is like difficult to really rigorously formalize in 110. There's more of it in stat 210. And it's always like difficult to kind of say what random is, even in like a philosophical sense. Like there are people who say like, it's not just people who say, it's very like big branch of philosophy that's like everything is deterministic, right? There's nothing truly random. If you had all the data and all the inputs, you could correctly predict everything. I think that's a pretty scary thought, but it's interesting to think about, maybe, that basically saying like you have no choice, like there's nothing random. So that's a philosophy discussion. In our purposes, we want to say like, okay, how do we actually like generate quote unquote random numbers in our R session? And, we kind of understand a sense of randomness from stat 110 as mapping from an experiment or sample space to the real line. And we know that these, I saw chat. Yeah, Skylar said, please no measure theory, which is like the more rigorous definition of how you define randomness. And I agree with Skylar. It just is not very rewarding and very, very hard. So we won't do that. But everyone here kind of is familiar with random variable mapping an experiment to the real line. And we know that randomness is governed by CDFs, right? The cumulative distribution function, we have the normal distribution, the PDF is the kind of the hump, and the CDF is integrating between the parts. We know that the CDF determines the distribution. If two distributions of the same CDF or two random variables of the same CDF, it's the same distribution. So, you can think of, we want to generate random values that map to those CDFs. The way that R does that is, we call setting a seed. So obviously before, when I ran the random number, R has some very complicated algorithms that generate these numbers to follow, if we did it a billion times, the CDF of a random uniform or a random normal. So it has these algorithms to do that in the background, spitting out numbers that will, in the long run, replicate these CDFs. But let's say you wanted to like get the same results, and I'm running a random uniform each time, getting a different result. If I do something called setting the seed of and I don't really know the terminology, but you're basically telling the like algorithm that generates a random number where to start, I'm going to get replicable results. So if I set the seed, I'm going to get random uniform 1, and let's say I run it again, I get 0.26. Now if I set the seed again and I run, I do another draw, I'm going to get the same value that I got above. And if I did argf again, I'm going to get this, this 0.26 value. So this is a really cool way, a one-liner basically is telling your random algorithm where to start. And it's a really cool way to get replicable results. If you're running a huge simulation with millions of random values, you can set it to someone and they can do the same results, check the same data. So that's what this like set seed is. Give me 1 second. I'm going to open the window more because I'm getting hot from all this talking. Okay. All right, so that's kind of how R generates random numbers. That was maybe more information than anyone cared about, but in case you're curious, I don't even know if it's a good explanation. In this case, we are defining our data set, and we have a bunch of things we haven't seen before. The biggest one is the matrix function, which, as you can imagine, also there's traffic outside, and if the traffic is too loud and it's affecting your hearing ability, just put it in the chat and I will close the window and find another way to cool down. So. Okay, so matrix will build a matrix of data. If you've taken linear algebra, you've seen matrices before. I think it's not called Math 21B anymore, but something like that. You've also probably seen it in Stat 110 or another example. The arguments of matrix are: the first argument is the data, the second argument is the number of rows, and the third is the number of columns. And that's why we have this n row n col. In this case, I'm taking 10 draws from an exponential, so that's this Rx. Sorry, I'm taking 50 draws, 10 times 50, that's the first argument. And I have a lambda, a rate parameter of 1/5. And I'm just using this round number to round the number to 1 decimal. Like if I did round 1 point, all that stuff, there's a Q in there. 1, it's going to round to 1 decimal. So I run this and I get this just random matrix. You can see 10 rows, 5 columns of just random exponential stuff. And I'm going to column bind the vector 1 to 10. So T is transpose, like flip this on its side. You can't really see, but it's a column here. Then I'm going to bind this column to this data. And what I get is first column is 1 to 10, and then the rest are kind of the random data. So hopefully, that wasn't too confusing, but you can see here we have this nice data set. And now I'm going to convert this data to a data table, which is like a very useful, just like form of data frames in R. You can, okay, this is a good hands-on example. R is telling me it cannot find the function data table. Why is that? It's because I don't have the data table library loaded. So here I have to do library data table. I don't have to install it because I've already installed it before. I do library data table. It gives me some, it gives me some messages. It wants me to do something, whatever, that doesn't matter. All that matters is that data table is in now and I can run this with success. And, my data looks the same. Data table is nice because it automatically puts names in I guess for version, column 1, column 2, column 3. I want to set the columns myself. So I do that with this names data and I define this vector. This little C is actually shows up a lot. It stands for concatenate. So like if you want to bind, numbers together into a vector, bind numbers together into a vector, you use that C thing to just, squish things together. It's used so often, so they just, abbreviate it to C. So anyways, this is my family. I did this example a long time ago. So I'm Matt, and then put myself first and then everybody else. So you can see now my data has the day and then, the people everywhere else. So you can imagine like this could be, miles walked, maybe not miles walked, 14.5, but some, numeric estimate, jumping jacks or whatever, number of days, and then the person. So like on day 3, Sam did 2.8 of whatever thing. Cool. So this is data that we're all very, this format is called the wide format, and it's very familiar. It's very natural. This is like Excel. We see this all the time. You have a column for each person, and then the ijth entry is the entry for the ith day and the jth person. We're going to be working with ggplot, which really likes data in the long format. So here I'm going to define this new thing, data long. And I'm going to melt my data, and it's an evocative term where it's like self-annotating. It tells you kind of what it's doing. We're taking this wide data and we're melting it down into a longer data. And here it's important to say that the ID variable is going to be day. We're going to melt around day. So I'm going to run this, and doesn't make sense at all what I'm talking about. Let's look at data long. Okay. So here we have, instead of, just like I promised, instead of having a bunch of columns, we have only 3 columns and a bunch of rows. So you can see the first 10 rows are days 1 to 10. The variable is Matt, that's me. And then the value is, my values for those days. If you compared that to, my column in data, you're going to see it's the same. It's just kind of organized in this way. If I scroll down a bit more, I have the same format. It's just, in this case, the variable is Tom, the person, who that is Tom, and day, and then the value in that sense. So, stop me if this doesn't make sense. It's a little bit weird to think about data. We would never show this, data this way to a human, but we're going to see why it's important for ggplot. Okay. So if you've done any plotting in R, you kind of you build the plot all at one time. And it's like making a picture, and it's like drawing a picture all at once, and you put the picture up. The nice thing about ggplot is you kind of build it in steps. And I like to think about it as putting blocks on top of each other. And I see a chat. Yeah, good question. What's the data table package called? It is just data. It is just data.table. My favorite package in R. Basically very good. It's good for large data. It's very intuitive. It's got some very powerful thing. One of the best supported things in R. So data.table is the data table package. Yeah, that's probably, I don't know if this will work. Let's just see if this will work with a matrix. Yeah, this should still work if you have, never mind. Yeah, it'll be a little bit funky with a matrix. So, get that data table. You can do it, but I just didn't do it in this case. So good question. Thank you, Skylar. Okay, so as I was saying, you want to build your kind of ggplot one step at a time, one block at a time. The first and most simple thing is just to do ggplot, which is the function. And then, these parentheses means I'm calling the function. It has no arguments, but, it just establishes this nice like gray field. And we're going to add on to that gray field one thing at a time. So the first thing we want to do, this is a separate call. I do this plus, and this is just kind of format, you put each new command on a new line. GG title, that's saying the title for ggplot. I'm going to run this and I'm going to see first ggplot. Nice. So I have a plot that doesn't have anything on it and a title, which is great. Okay. Now I have a little bit more of a complicated call. So I'm going to run it and then we're going to talk about it. Okay. So here it's ggplot and then the GG title, first ggplot. But here, here I have this AES thing, which means aesthetics. These are the like aesthetics of the chart. I'm saying I want to put day on the x-axis and y and value on the y-axis. And remember what data long looks like. We have day here and value here. So you can see here, as we wanted. Sorry, my Zoom thing keeps getting in the way. As we wanted, we have day on the x-axis and value on the y-axis. What's missing in this chart? Oh, good question. Sorry, I'm just looking at it. Okay. So first, good question, Elizabeth. Elizabeth asked, got an error saying that melt function couldn't be found. I believe that's in the reshape2 package. You can install packages reshape2 and then run library melt to get that. That should work. There might be another version, but you can see in this case, I typed double, yeah, no problem. You can see in this case, I typed double question marks to see where it could be found. So that's a really good question. Sorry, Mel is probably not, included in your, I should have known that. Okay, so what's missing on this chart? Easy question, layup question. Yeah, the data, exactly. The data is missing. Nice chart, but there's no data. Data points, exactly. Great job. Everybody is still awake, which is more, honestly, than I can say for a meeting I was in earlier today. So what we're going to do is add, let's just do it in this version before we do fancy stuff. We're going to add the points. So see how I do another plus, and then geom point is saying, make our geometric points, according to these aesthetics. And I print out the data here. So look at that. We have our data now, and this is nice. We have our dots. We can do geom line. Oh, it's going to look a little bit weird. But geom point is a bit better. So what's not great about this chart? Given that, remember, this is the data we have. What's like not great about this chart? No names. Thank you, Stephanie. So, this is a huge number. We don't know who did that. And, these are all black dots. It's tough to identify who did what. And this is where ggplot, even though this, you're probably like, this is so annoying. Why do I have to do all this stuff, melt the data, all this stuff. This is where ggplot is pretty powerful. We're going to add into our AES call, we have our X and our Y, and we have our color kind of command. And this, we're going to say, we're going to color this plot by variable. And remember, in data long, the X is day, the Y is the value, and we want to color by the variable, which in this case are the names of the people. And I'm going to run this chart. Awesome. So we have a kind of a fancy plot here. But first of all, the most important thing we did was we colored by person. So now you can see a little legend pops up automatically on the right. You can see this little orange thing. That's my line. That's these lines here. And they're just colored by person. You can see Tom started off strong and then maybe went down. So that's really nice. There's a bunch of other little things that I added here to kind of make this prettier. First of all, I have my geom line. That's these things. I set alpha equal to 1/2. That's basically saying how dark the line is. Maximum of 0, maximum of 1, minimum of 0. So this is saying make it half dark. There's the GG title. This geom smooth basically adds a trend line. So, these curved lines, that's the trend line. So I kind of faded the actual data in the back and made these nice little trend lines. This SE equals false is saying don't include standard error bands, because if I include the standard error bands,
you're going to see it's a little bit ugly. You know, these are like you're going to learn more about confidence intervals in 111, obviously, but these are like the 95% confidence intervals for the data. I think it's kind of ugly, so I just take it out. This is just telling us what to label our x-axis, our y-axis. This is giving us a horizontal line, H line, setting the y-intercept at 0. And this is telling us what theme we can use. And this is like a pre-packaged theme. It might not work in your sessions. You might need to do install packages and then library GG themes. So, you know, you can always do that, but you can also take it out. You can just like take out that part if you want and just run your normal ggplot like this. But you can kind of tell, like, you know, this all is just adding things onto one another. I can comment out a line and run it, and now I'm not going to have the smooth values, but I'm just kind of going through and adding on things to my ggplot. Okay, so that's pretty much all we're going to talk about for ggplot. The main thing is like melting the data from wide to long. Anyone have questions for, you know, this kind of visualization? Yeah, good question, Michael. Michael asked, what does geom smooth do? This adds a trend line. So the actual data, let me take out the trend line at first, and let me just make the alpha equal to 1. This is our actual data. You can see it's spiky because the numbers jump each day. And to make it even really clear, let's make these into points. So this is our actual data. If I add geom smooth, I'm adding a trend line. So it's kind of like you can think of it as a rolling average. You know, a rolling average of the terms, and now you can see like Tom's, instead of these points, he's got this nice smooth like rolling average instead. So just a way to yep, really good question. So another question is, Michael knows that this says using method low or law. I actually don't know what this stands for. That's a really good question. There's a lot of ways to, you know, create your trend line, rolling average, this lowest thing. You know, if someone knows, you know, let me know. But this is like some sort of rolling way to do it. You know, you can specify the method if you want. Another one that I know is linear model. So instead of like this thing, you can do a linear model for your smooth, and now you can see instead of something that goes up and down, it's just like a straight line. So that's a really good question, and thanks for asking that. You can specify what you want there. Yeah, no problem. And that's something that I'm definitely not. I like more of the like theoretical probability stuff. So I'm not as good at the like rolling averages, but that's a very good question and something that's useful. So okay, cool. So let's move on to do some optimization. I took Stat 111 in 2015, so 7 years ago, which is disgusting. I took it with Kevin Rader, who many of you probably know. He was also teaching 110 that fall because Joe was on sabbatical. And we did a lot of optimization. You're taking it with Neil Shepard. I'm not sure if you'll do as much optimization. It's good to know just in case. They'll definitely use it at some point. So we're going to do it here. So the first thing that we're going to do in this part is define our own function. And we've been working with all types of functions. We've been working with mean, ggplot, even the concatenate function. What if you want to define your own function? You know, you're going to run a bunch of code over and over. Instead of copy and pasting, you can like write your own function yourself and then call it. And it's easily scalable. So the format for this is, you know, you're gonna want to give it a name. You're going to assign something to it, just like we assign numbers to variables. I think it's good convention to name things like capital fun, super fun, capital FUN to remember that it's a function, underscore, and then the name of what you want it to actually be. And you know, this is just useful because like I have X and then I know that X is not a function because it doesn't start with FUN. I know this is very clearly a function. And that's just a good like naming convention. So we assign function to it. You can see it turns orange, special thing in R. We're going to say this function takes argument X. You know, we can specify as many arguments as we want, but in this case, it just takes X. And then inside the curly brackets, just like the for loop, we're going to do all the code that we want to do. And in this case, it's just one line. Once you have all the code you want to do, you're going to return, you know, it's going to be the output of the function. So I'm going to define this function. Now it's in my memory. And if I just run, you know, if I just put this into R is going to tell, oh, well, this is a function. It takes value X and it returns this. Does anyone want to tell me? Oh, and I was playing with this before, so let me unplay with it. Wait. Sorry, Okay. I was messing with it. So the name didn't match what it's doing. Does anyone want to tell me what this function is going to do? So if I type this for what's going to return? Oh, I see we're losing participants. We're down to 66. That must be boring, everyone. Oh, okay. So I see a good question. But first, let's answer this. What is this going to return? -2. Thank you, Elizabeth. Exactly. -2. Thank you, Clara. Get this going to run -2. You can tell by the name, this is function negative square root, and you can kind of tell in the function itself. We're taking the square root. This sqrt means we're taking the square root of x, and then we're applying the negative to it. So we're going to return -2. So that's exactly what that does. If you understand that, you understand the basic principles of a function. I could define this so it had a default, a default argument. I'm going to say the default here is x equals 4. And what's nice about that is if I now don't enter an argument, it's still going to run with 4 as the default. I could also specify like more arguments. Say I want to raise this to the power of y. You can get as complicated as you want. So on 410, going to get that's -2 to the power of 2, or yeah, -2 to the power of 10. Maybe there's some negative, some reason it's negative, but we get 10 to the 24, as you can see. So was okay. I have a good question from the previous part. Is it possible to save a ggplot as a variable for access later? Absolutely, that is possible. Really good question. So usually you've seen it saved as p. I can save this as p, nothing ran, but if I just type p, it's going to put the plot up. That's a good way to save it for later. You can save it as an image. You can stack it with other plots. So what's nice about ggplot is you can save it like an object. So really good question. Okay, so we tested out the function. Oh, sorry, I got to define this again. Notice I ran it and it failed because argument y was missing because I had it defined to take in 2 arguments. So that's nice. It doesn't work if we don't specify the argument. I reran it. Now it's going to work. What's going to happen when I run this function on this like character high thing? What's going to go down? Feel like I'm a Peloton instructor. It'll scream at you. Exactly. Thank you, Michael. It'll scream at me. So I will say hi to the computer, and the computer does not like that. It says error, non-numeric argument to mathematical function. A lot of times these errors are totally uninterpretable. In this case, I think that's very interpretable. We have character, it's a character, hi. It's a non-numeric argument, but we want to do a mathematical function, square root, so that's not going to work. So that's what happens there. Okay. Now we're going to do, first I'm going to create this thing X. It's this command is saying seq is sequence from -10 to 10 by 1. So that's just counting from -10 to 10 by 1. You can see I have all the integers from -10 to 10. And then I want to basically run my function over this vector X. To do that, there's a lot of ways to do that. We use a for loop. Another way is using applies, which I wanted to touch on here because you might not do them that much in 111, but they're very powerful and widely used in R. Basically, in this case, we're using sapply. Looks like sapply, but it's sapply. We're applying this function, fun negative square root, over X. And we know that X is this vector from -10 to 10. So we're going to apply this over X. Okay. And that's going to be Y. And okay, can anyone explain to me what just happened? Square root of a negative value. Thank you, Alan. Exactly. You cannot take the square root of a negative value. Maybe it's imaginary. R is not going to be able to handle the square root of negative value. So all the values up to 0 are NaN. That's worse than not available. It means like couldn't calculate it. What are you doing? And then these other values are kind of what we want. But the important thing here is that we applied this function over all of our values for X, which is cool. I'm going to change this just to square root, just so we can actually get values. Oh, sorry, that's dumb. Okay, square root of X squared will be what we want. Yeah, okay. Let's do square root of X cubed, so we don't just get like the same. It's not the identity function. Okay. Oh God, I keep forgetting cubed is negative. Okay, sorry, this is so embarrassing. Okay, now I have these numbers are the square root, so 100 is the square root of -10 to the 4th. So basically, it's negative 10 squared. You're probably laughing at me at home, but so that's how, yeah. So one more cool thing, I did that so we could talk about how applies work. You can apply over values, lists, tables, whatever. The other cool thing about R is that what we did is actually unnecessary. R is vectorized, which means you can like do an operation over an entire vector, no sweat. So if I wanted to just run y, run negative square root over x, I would get the same result because R knows that I apply this function over this vector. So we're going to talk more about vectorization in a bit, but that's just something we can see here. You know, it's not necessary to do this S apply in this case. Okay, we're going to organize this stuff in a table. So here we have our data table, x to y, and now we're going to actually want to plot it. So you can see I have this nice plot here. Okay, I'm going to flip this over because it's going to help with our optimization. Sorry. Okay, so I just did the negative of that. So now I have this nice plot here. You can see it's a GG plot. The data, my aesthetics, X is the X value, Y is the Y value. I'm adding points and I'm adding labels for the X and Y axis. Okay, so, you know, your whole life you've been doing optimization. You know, maybe you've taken more advanced classes for it, but in the most simple version, you derive something, set it equals 0, solve to find the optimization, to find the optimal value, the minimum or the maximum. Even more simple, you look at the chart like this. I think it's clear that y f of x is maximized at x equals 0. But we want to do this in R, and we want to do this because even though this is a simple example, we're going to have more complicated examples we want to be able to optimize. So as you might expect, the canonical optimization function in R is optim, short for optimize, and it has all of these arguments. This is one of the hardest parts of 111 for me. If you get comfortable with optim, at least the version I took, it's going to be a lot easier. So the first argument is just the function you want to optimize. In this case, that's obviously, you know, the thing that we have defined here. And this par is telling us, man, I haven't done this in a while. So I'm pretty sure this is telling us start looking at 0. So you're telling your optim, look to the ends of the earth and beyond, from negative infinity to infinity, look for what the optimal value is, but start at 0, right? And in this case, like we have a very good prior guess as to what the answer is. We know it's 0, so we're going to tell it to stop at 0. Let's tell it to start at -5, just to make it a little bit harder for it. And then this control thing, basically by default, optim minimizes. We want to maximize, so we set this weird control list fn scale, function scale. We're scaling the function by -1, so we're maximizing instead of minimizing. We can also restrict the space we want the optimizer to look over. We want it to look from -10 to 10 because like we only have values from -10 to 10. You can do this in real life if you're pretty sure, the maximum is between -10 and 10. You can widen that or shorten it. Obviously, it's going to be harder to do for the optimization if you can't. But yeah, so we're going to run this, and that's kind of our setup. And let's actually just look at the output. Oh, did I mess something up? Okay, good. So this is a little bit, anticlimactic because it's all zeros, but this par is the final answer. It's the result. It found it at 0. So it found that 0 was the maximum. This $ value thing is saying that your function evaluated at the maximum 0 is 0, which we know to be true. So the optimal x is 0 and the optimal y is 0. And then, this stuff just gives us some more like mathematical, like did it converge, all that sort of thing. We can make this way more challenging and like look from -10,000 to 10,000. And let's say we start at -9999. And it still works because this is a very simple function and it's still going to be able to find it. So that's pretty cool. Okay. Let me just, sorry guys. Originally I had defined this function, which was like shifting x by 1, then taking the negative. And I had run it over just so the output makes a little bit more sense. In this case, this function that you see here is going to be maximized at 1 because it's the same thing. It's just shifted by 1. So obviously the maximum value is 1. So this output looks a little bit more exciting, even though it's the same thing. The optimal value here is 1. And this is saying the value at 1 it looks like, oh no, it should be 0. This is basically 0 because this e negative 32 means that it's negative 4.9 times 10 to the negative 32. So 0 with machine precision is what this is. So it's 0, and it converged. And the last thing I want to show you is this is the same function as above, but it's going to be negative, the negative version. Can anyone tell me what's different about this optim call? Sorry, I know I've been talking a lot. It's a bit of a silly question, so no worries if nobody finds minimum. Thank you. Awesome, Dennis and Richard. Thank you. So this is going to find the minimum instead of the maximum because I didn't include this control list FN scale thing. By default, it's going to find the minimum, but that's fine in this case because we basically did our FN scale -1 here. So it's going to give me the same result, 1, and converges at 0 with machine precision. So that's, it sounds silly, but there have been many hours late at night doing my PSET where I have it flipped and it's not working. If I tried to find the optimum for this, thing, oh, sorry, someone chatted me. Okay, that's a good question. So I'll answer that in 1 second. Thank you, Skylar. Okay, so in this case, I'm doing the wrong thing. I'm maximizing the negative, and here, obviously the minimum or the maximum value is going to be -10. But that's not what I want. So make sure you get your order right. So Skylar asked, how does Optim deal with multiple optima? That's a really good question. I used to know the answer to that, and I don't use Optim too much anymore. So that's something that a Google can help with. A Google search can help with. Something that you can always do is you can always have, if you're familiar with machine learning or something like that, you have some optimization problem, you have a loss function. And if you can get that loss function down to one number, let's say you have a couple of constraints, okay, let's say here a big constraint is if X is greater than 5, we're going to return okay, let's say you have a constraint that, you want to maximize Y, but you also want X to be greater than 5. One way you could do that, this is a very sloppy way, but it'll work, is in case that X is greater than 5, return a very negative number. So the Optim will find out pretty quickly you don't want X to be greater than 5. That's one way to do it. If you have different other optimal, you want to maximize this and this, you can add them together, you can multiply them together. These are all it's a very good question. These are unscientific ways to answer it. There probably are better ways to do it in R, and if you take an optimization class, which I haven't, you may know better ways. So that's a very good question. You probably won't face it too much in 111. Okay, any questions on optimization before we move to simulation? Okay. All right, so moving into the simulation part, this is what I think is the cooler stuff. Something that's very useful. I taught 110 for 2 semesters, and I would tell my students, it's so useful if you can use R, because every 110 homework problem, exam problem, practice problem, you can simulate it on your computer and see what the answer is. And not a lot of classes are like that. You probably get that in 111 as well, where you're it obviously doesn't do the problem for you because you still have to do it analytically, figure out, the lotus or whatever to do it. But at least you can check your answer and say, okay, I got the expected value. The conditional expectation is 7. Does that check out when I simulate it? So here we're going to practice our simulations by doing some 110 problems. Who remembers the bank post office result? If you haven't blocked it from your memory, just give me so I'll give you the, hopefully I don't misrepresent this. So you're at a bank, wait, I'm going to mess it up myself. Basically, you have 2 gammas, 2 independent gammas. In this case, I have X and Y, and they are, 2 different weight times. You can remember of gamma as the sum of exponentials. And then I have this ratio of, I have the result there. I have this ratio of okay, I'm doing a really bad job explaining this, but you have the first gamma, this X, and the second gamma is Y. You can see I've defined the parameters here. And then I have this ratio W, which is the time you spend at the fraction of time you spend at the bank, if X is the bank and Y is the post office. And who remembers the big result between X and W? Sorry, that was a really bad explanation. W is beta, exactly. W is beta. It's like I think it's beta AB, if I remember correctly. And what about the relationship between W and X? Thank you, Gerald. That's correct. What about the relationship between W and X? Okay. Independent. Thank you, Alan. Yes, exactly. So it doesn't. It's pretty unintuitive. It's like, if I've spent a lot of time at the bank. Wait, did I? Yeah. Okay, I may have said this wrong. This is really embarrassing if so, but I'm pretty sure that the fractions are independent, because if I spent a lot of time at the bank, you might be like, okay, that means that W should be large because I have, a large fraction of time. But the intuition behind this is like you have an X in the numerator and the denominator. It's not a very intuitive result, and you proved it in 110 doing some like transformation Jacobian type thing and show that the PDFs factor out. But that's kind of the result we see here. So I really butchered that, but I'm gonna talk about this. So set the seed. Remember, that tells us like replicable random values. We're setting the seed of 0. We're gonna say we have 10,000 simulations. And here I'm setting the parameters A and B and our lambda. We generate our gammas and we generate W, which is our fraction of time. You can see that X is just this vector of 10,000, length 10,000. You can think of these as minutes spent at the bank. And then W is going to be, this vector of fractions. So we said this was independent. This is a good example of like, okay, Joe, I don't believe you. I'm actually going to simulate it myself. And what's cool is if we run this core, which stands for correlation, we're going to see that of course, X and wait, I'm sorry. You guys are probably laughing at me at home. Okay. Of course, X and W are dependent, but what's independent is the total time you spend and the fraction of time you spend at the bank. So that is embarrassing. It's too bad this is being recorded. No, I'm kidding. So of course, the total time you spend at the bank and the fraction of time you spend at the bank are very dependent. You have a very high correlation because the more time you spend at the bank, the more time overall your fraction is going to be. But what's interesting is that the total time you spend is independent of the fraction of the bank. And if I run that correlation, I'm going to get a correlation of basically 0. This correlation of basically 0 does not prove that these things are dependent, of course. It's a necessary but not sufficient condition for showing independence. So you can tell I am very rusty. I'm sorry about that. But this is an example of very simple simulations with random variables to do that. Okay. And Gerald said a really important thing, which is that W is beta. And it's true, we have that W is beta with parameters A and B. So I'm going to run my own independent beta, save it to Z, and I'm going to do this nice ggplot to show that. So in this case, let me show the code that I'm doing. In this case, I set up my ggplot. I have my histograms. My histograms, I'm going to have Z, which is the beta that I generated, and W, which is the fraction of gammas that I generated. And I'm going to they're each going to have like 1/2 shading in red and blue. And if you look at that, they basically perfectly overlap. Again, this isn't a proof that they're the same, but you can look at this and say, okay, I'm pretty sure that's that's beta. They're a little bit different at points, but they're pretty close. And this is cool, right? Because you generated these with R gamma, you generated this with beta, but due to our beautiful 110 results, they are the same. Okay. Awesome. So now let's do the chicken and egg result. So hopefully I'll do a better job of not embarrassing myself here. Chicken and egg, you can recall that a chicken lays n eggs, where n is Poisson. In this case, we're going to say Poisson lambda. So the chicken it's expected to lay 7 eggs, but it follows a Poisson distribution. So we're going to generate that. And then each egg hatches with probability 1/4 independently. So then X is let's just scroll back up to the beta stuff. Sorry, before we get into the next thing. I'll talk about it one more time. Sorry, I butchered everything. So again, we're setting the parameters for the gammas and then the lambda. So remember, like, this is saying that the first gamma is the sum of 3 exponentials, each with parameter 1. This is, 7 exponentials, each with parameter 1. I generate the gammas with X and Y, and then W is the fraction X over X plus Y. So if this is time at the bank and this is time at the post office, this is the fraction of time at the bank post office. Of course, I messed it up, but The correlation of fraction of time you spend at the post office and the amount of post office time is not zero. But the correlation of the total time you spend out and the fraction of time you spend at the bank is zero. They're independent. The only two distributions that this works for, I believe. And then, we're just checking that this W follows a beta AB distribution. So we're generating, we're generating a bunch of beta ABs. Oh, sorry. Thanks, David. Thanks, David. Thank you, David. I appreciate that. I didn't do a good job explaining it because I messed up the independence, but thank you. Okay, awesome. So let's do the back to the chicken and egg. So again, you have N eggs, and then each egg has probability 1/4 of hatching independently, 3/4 of not hatching. So here I have kind of my values. Now, you have your N. These are a bunch of different simulations. Like in this case, the chicken hatched 7 eggs. In this case, 12. In this case, 5. It's not immediately clear how you're going to get the X and Y out of this, right? In this case, there are other ways, but we're going to use a for loop. So we're going to loop over 10,000 times, N sims times over N. And each time we're going to actually use a binomial and generate how many eggs hatch. So on the ith try, we're going to do R binom. This is saying do one, run it once. So binomial NP, one draw. N is going to be the ith experiment we've run. So, if it was 885 and I would be 8, the chicken laid 8 eggs, and, each egg has probably 1/4 of hatching. And then the ith element of Y, it's going to be the number of eggs minus the number of eggs that hatched, which just by definition, X plus Y has to equal N because the eggs either hatch or don't hatch. So I'm going to run that, jump in if this doesn't make sense. Okay. And you can see let's just look at the head X and head Y and head N. And you can see that, first of all, X is smaller than Y, which makes sense because the chickens sadly don't have a very high probability of hatching. You can see that, X and Y adds to N, which is what we wanted. In the first case, the chicken laid 8 eggs, 3 hatched, 5 didn't, and it goes from there. So who can remind me what the two cool results for chicken and egg are, as I try to remember them myself? X and Y are independent. Thank you, Joe. That is the big takeaway. That's exactly what's the distribution of X and Y? Poisson, exactly. Poisson specifically with parameter P times lambda. It's capital P, but I sent that to Skylar instead of the whole group. But okay, so first of all, the first kind of result is that X is going to be Poisson with, yeah, exactly, X. Poisson, so it's going to be Poisson P times lambda. So this P and this lambda, I'm going to generate just like we did before. R Poisson means random Poissons, N sims times, lambda times P. So that's, 1.75. Going to generate a bunch of those, store that in my Z. And just like before, I'm going to plot, my values versus the actual X we observed. And you can see, again, this should make you pretty confident they are the same. You get kind of the same result. So that's really good. And then the independence result is also super important. So let me scroll down to that. So correlation of X and Y, intuitively, it's like they should be dependent. If I know that 10 eggs hatched and I don't know anything else, that, I guess that should tell me that more eggs didn't hatch because 10 did hatch. But, there's two main factors at play. One is that a higher X means that N is probably higher, but a higher X also could mean that there's just a higher fraction of eggs that hatched. And in the Poisson case, the Poisson binomial case, they completely offset and there's no information provided, which I think is the only pair of distributions that it worked for. And again, if I do the correlation, I'm going to get basically 0. Again, not a proof. This is not a formal proof of independence, just like a good sense check. And, remember, X and Y conditional on N are very much dependent, because if I know that 10 eggs hatched and if I know that 10 eggs hatched and I know the chicken laid 15 eggs, I know with certainty that 5 eggs didn't hatch. So if I run this piece of code, this is saying correlation of X given that N equals lambda, which is 7, given that 7 eggs hatched, what number am I going to get if I run this? Any guesses? Correlation, any number between -1 and 1, uncountably infinite options. So I'm going to get -1 because these are perfectly negatively correlated. There's a perfect relationship between the two, and it's a negative relationship, so you'll get -1. Awesome. So any questions in simulation before we move to the last topic before we open to general questions? Awesome. Okay, let's talk about R Markdown, which hopefully everyone is relatively familiar with. I highly recommend this for actually, actually turning in your homeworks. I know Harvard back in my day, when I took 110, I actually wrote it on pieces of paper and handed in my PSET, just crazy. And I think COVID has really accelerated the turning things in online. You can still write it out and scan it, but I highly, highly recommend learning how to LaTeX. Hopefully everyone's familiar with LaTeX. Overleaf is a really good, resource for storing all your LaTeX stuff. And then for stuff where you're going to be running R, learning R Markdown. So we're looking at an R Markdown file here. It's similar to our R scripts, but it's actually, this is sort of it allows us to do a kind of presentation. So I'm going to just compile this so you can see the final result, so we can, sorry, the sharing is weird. Let me see. I'm just going to show this, and then now you can see me, and now I'm going to share my, okay. Nice. So this is the result. This is what we got. And this is pretty cool. It looks like something that you could turn in. You have some text here. You have some R code here. You have the output. You have a nice title. You have a nice plot here. Very clean, very nice. I even have a link here. If I click this link, it would open in Google Chrome, and just a really cool way. And you could clean this up and make it prettier, but this is a good way for you to turn in your kind of homework. And let me go back to R now. Okay. So how do we do that? It's pretty simple. When you open new file, you're just going to select R Markdown instead of R script. It'll just show you what it looks like. It'll automatically populate a lot of the stuff that you need, and you can adjust it from there. So that's nice. And then you just, you do what you got to do. So when you type, it's just going to show up as text. Here I have, this is how you make a link. You do this little brackets, and then you put the URL you want there. The link I've included here, which is in all the code that you have, and you can Google it as well, is an R Markdown cheat sheet. Really useful source, how to link stuff, how to make stuff bigger, smaller. If you run code, if you want to show the output, don't want to show the output, want to show the code, whatever. Someone asked a good question about that earlier. And the nice thing is, first of all, you can go right into LaTeX. So hopefully everyone, this is not going to be any LaTeX stuff. Hopefully you're familiar with LaTeX, but if you wanted to do, just like we'll do the standard normal. If you want to type the standard normal, you can go right into math mode with your dollar signs. It even pops up here, and math mode works. You do it with single dollar signs as well if you want to do it inline. So it works with LaTeX, and it works with R, which is really cool. To enter R mode, you just type these three back apostrophe things, curly space, curly bracket R, and then you go into R mode, and you can run R here. And you saw in the output, you're going to see this R stuff. So, you can very easily see how, problem one, this is problem one, here's the code. You can see how this would work for your, for the kind of stuff that you'll do. And if you want to compile it, you just hit this knit button, and it'll all knit together. And this is stuff that you're going to learn on your own and kind of Google how to do it, but I just wanted to show you quickly how this works. If you spend a little bit of time now making a little report in R Markdown, it's going to be a lot easier for 111 and for the rest of your classes. The last semester, I took 3 classes. All of the homeworks were done entirely in R Markdown. Part of it is because I'm forcing it because I like R Markdown, but it's extremely useful. Okay, so that is all I have. I think 90 minutes is a good amount of time. Other than that, it's hard for me to pay attention past that if I'm learning stuff. So feel free to ask questions about R Markdown, or just in general questions about the statistics experience, what it's like to major in it or concentrate in it, what it's like, job search afterwards. And even, I'm back in school now. If you have questions about further schooling, that sort of thing, feel free to let it fly. And thank you all for coming. Of course, this is obviously, it's a Friday during J term, so it's a lot of work, and hopefully this was enjoyable.